Welcome to a journey through winter's most beautiful mystery, the snow and snowflakes. Just as snow settles gently upon the earth, let yourself settle now into comfort, finding a position where you can truly rest. Imagine you're preparing to watch the first snowfall of winter, that moment when the world grows quiet and peaceful. Allow your body to become still, like the hush that falls over a landscape as snow begins. There's nothing you need to do right now, nowhere you need to be. You can simply rest and listen as we explore together the remarkable story of snow, how it forms in the cold reaches of the atmosphere, and how each tiny crystal becomes a unique masterpiece of ice. Take a deep breath in and let it out slowly. Feel your shoulders drop, feel any tension beginning to melt away. You might close your eyes now, or let them rest softly on a single point. There's no effort required, no need to concentrate too hard. Just let the words wash over you like gentle snowfall, settling softly into your awareness. Tonight, we're going to travel together through the science and beauty of snowflakes, those tiny crystals of ice that transform our world each winter. We'll explore how they form, molecule by molecule, in the cold heights of clouds. We'll discover why each snowflake is unique, yet all share the same hexagonal symmetry. We'll follow their journey from sky to ground, and learn how they shape landscapes, ecosystems, and human life. But this isn't just a catalog of facts. This is a story, a long, gentle story told in a way that mirrors the slow, peaceful process of snow itself. Just as snowflakes accumulate gradually, building up layer by layer, our story will unfold slowly, each idea flowing naturally into the next. There's no rush, no urgency. We have all the time we need. You don't need to remember everything you hear. You don't need to stay awake for every word. In fact, the purpose of this journey is to help you find rest. If your mind wanders, that's perfectly fine. If you drift in and out of sleep, that's exactly as it should be. The story will continue, like snow falling through the night, whether you're listening closely or floating in dreams. Think of this as a meditation on winter's beauty, a celebration of the intricate patterns that nature creates. Through understanding how snowflakes form, we touch something profound about the universe itself, how complexity arises from simplicity, how beauty emerges from physical law, how infinite variation springs from fundamental order. Snow is patient. It forms slowly, falls gently, accumulates grain by grain. Tonight, we'll match that patience. We'll take our time. We'll breathe slowly. We'll let the rhythm of falling snow become the rhythm of our rest. As we journey through this story, you might notice your breathing slowing down, becoming deeper and more regular. You might notice your body becoming heavier, more relaxed. You might notice your thoughts becoming quieter, less insistent. These are all signs that you're settling into rest, and they're all welcome. Let yourself relax as deeply as you can. The story ahead is long enough to carry you through the entire night, but there's no expectation that you'll hear it all. Most people will drift into sleep long before the end, and that's perfect. The story is here to accompany you, to give your mind something gentle to follow as you transition from waking to sleeping. Once you're deeply asleep, the story will simply be a soft presence in the background, no longer needed but doing no harm, like moonlight through a window or the distant sound of wind in trees. Now, let's take one more deep breath together. Breathe in slowly and release. Feel yourself letting go of any remaining tension, any lingering concerns about the day. For now, there is only this, your breath, your body at rest, and the story of snow that's about to unfold. Imagine, if you will, that it's evening, and snow is beginning to fall. You're warm and safe inside, looking out at the winter world. Each snowflake catches the light as it drifts past, appearing then disappearing into the growing darkness. The world is becoming quiet under its blanket of white. And you, too, are settling into your own quiet, your own stillness, your own peace. We're about to begin our journey into the clouds, to witness the birth of snowflakes, to understand their structure and their story. But before we rise into that cold, crystalline realm, take one final moment to simply be here, breathing, resting, preparing for sleep. The story begins now, but you can let go whenever you're ready. There's no need to hold on, no need to stay alert. Let the words carry you like snowflakes carried on wind, gently, inevitably, toward rest. Let yourself settle into comfort as we begin a gentle journey into the clouds, where winter's most delicate creation takes form. Close your eyes and imagine you're floating upward, rising through the cool evening air, leaving the ground far below. High above the earth, where the air grows thin and cold, our story begins in a place where temperatures drop to -15 degrees Celsius or lower. This is where snowflakes are born, in the quiet realm of clouds where water exists in a state of patient waiting. The cloud around us is filled with countless tiny water droplets, each one so small that a million of them together would barely fill a teaspoon. These droplets remain liquid even though the temperature here is well below freezing, suspended in what scientists call a supercooled state, waiting for something to help them transform. Drifting through this cloud, we encounter the essential catalyst for snow formation, ice nuclei. These are microscopic particles, no larger than a grain of pollen or a fragment of dust, that have traveled here on wind currents from distant places. Some began their journey as volcanic ash from mountains thousands of miles away. Others are particles of clay lifted from desert sands, or tiny fragments of minerals carried from ocean spray. Each particle holds a special quality that allows water molecules to gather and freeze around it, like a seed that will grow into something beautiful. When a supercooled water droplet meets one of these ice nuclei, something remarkable happens. The water molecules begin to arrange themselves into a crystalline structure, forming the first tiny core of what will become a snowflake. This transformation releases a subtle warmth, as the water shifts from liquid to solid, molecule by molecule, building a foundation of ice no wider than a human hair. The molecular structure that forms is always hexagonal, a six-sided shape dictated by the geometry of water molecules themselves. Each water molecule consists of one oxygen atom bonded to two hydrogen atoms, forming a shape like Mickey Mouse's head. When these molecules freeze, they naturally stack together in hexagonal rings because of the angle of the hydrogen bonds, which is precisely 120 degrees. This is why every snowflake that has ever fallen, and every snowflake that ever will fall, has 6 sides or 6 points. It is written into the very nature of water itself. As our nascent snowflake begins to grow, water vapor molecules from the surrounding air collide with its frozen surface and attach themselves, adding layer upon layer. The snowflake grows slowly at first, adding perhaps a few hundred molecules each second. The temperature and humidity around the snowflake determine exactly how it will develop. At temperatures just below freezing, around -2 degrees Celsius, snowflakes tend to grow as thin, flat plates. But at colder temperatures, around -5 degrees, they extend into delicate needles and columns. The snowflake begins its descent through the cloud, falling gently through regions of varying temperature and moisture. As it falls, it may enter a layer where the temperature is around -15 degrees Celsius, the perfect condition for creating the most elaborate star-shaped snowflakes with intricate branches and patterns. Here, at each of the 6 corners, arms begin to extend outward, reaching into the cloud like the branches of a tiny tree. The corners grow faster than the flat faces because of subtle differences in how water molecules attach to different parts of the crystal structure. Each of the 6 arms experiences nearly identical conditions as the snowflake tumbles slowly through the air. When the snowflake passes through a pocket of higher humidity, all 6 arms respond similarly, perhaps adding a cluster of smaller branches. When it enters drier air, growth slows uniformly across all 6 points. This is why snowflakes are symmetrical. Each arm is recording the same journey through the atmosphere, building an identical history in ice. But here is where the magic of uniqueness emerges. Though the 6 arms of a single snowflake grow in symmetry, no 2 snowflakes follow exactly the same path through the clouds. One might drift through a slightly warmer pocket of air while another passes through a region of higher moisture. One might tumble more rapidly while another floats gently. Each subtle difference in the journey creates different growth patterns. When you consider that a single snowflake might contain a quintillion water molecules, all arranged according to the specific path that one crystal traveled through the atmosphere, the number of possible combinations becomes effectively infinite. As our snowflake continues to grow and fall, we notice how its structure reflects its biography. Perhaps it developed a thick center plate during a period in relatively warm, moist air near -5 degrees. Then it fell into colder air at -15 degrees, where long, delicate arms sprouted from its 6 corners. A brief pass through even colder air at -25 degrees added tiny ridges along each arm. The snowflake has become a frozen diary of its descent, each feature a chapter in its journey through the winter sky. The process of growth continues for perhaps 20 minutes to an hour as the snowflake makes its way through thousands of feet of atmosphere. Water vapor continually deposits onto its surface in a process called deposition, where water transforms directly from gas to solid without ever becoming liquid. This is different from frost, though similar in principle. The snowflake is essentially a piece of frost that formed in the sky and never touched the ground until its journey was complete. Some snowflakes grow in simple shapes, hexagonal plates like tiny dinner plates made of ice, or simple columns like miniature pillars of glass. Others develop into needles, long and thin as threads. The most complex are the stellar dendrites, the classic star-shaped snowflakes with elaborate branching arms that look like tiny frozen ferns. These form in the narrow temperature range around -15 degrees Celsius when the air is also fairly humid, providing abundant water vapor for construction. As the snowflake grows larger, it may begin to fall faster, perhaps half a meter per second, still a gentle floating descent. Its 6 arms continue to elaborate, with side branches sprouting from the main branches, and sometimes smaller branches emerging from those. The pattern of branching follows rules similar to those that govern the branching of rivers or the growth of trees, patterns that appear throughout nature wherever things grow and divide. Throughout its formation, the snowflake remains nearly transparent, though it appears white to our eyes. This happens because the surfaces and angles of the ice crystals scatter light in all directions. When billions of snowflakes accumulate on the ground, they create countless surfaces that scatter light, which is why fresh snow appears so brilliantly white despite being made of clear ice. A single snowflake is actually quite transparent, like a tiny fragment of glass, but together they create fields of white that reflect up to 90% of sunlight. Deep in our journey through the cloud, we observe how different conditions create different forms of snow. When the air is extremely cold, colder than -30 degrees Celsius, ice crystals grow very slowly into simple shapes, often tiny prisms or hollow columns. These are the snowflakes of the coldest winter days, the ones that fall in the far north where the air itself seems to crystallize. They create a fine, powdery snow that squeaks underfoot because the crystals are so hard and angular they grind against each other when compressed. In slightly warmer conditions, still below freezing but closer to zero, snowflakes might develop as thin plates or might even begin to aggregate, with several crystals sticking together to form larger composite snowflakes. These are the large, wet snowflakes that fall near freezing temperatures, the ones perfect for making snowballs because they're partially melted and sticky. Sometimes a single snowflake you catch under glove is actually dozens of smaller crystals clustered together, their arms interlocked like pieces of a three-dimensional puzzle. The journey of water that becomes snow began long before the snowflake formed. The water molecules in our snowflake might have evaporated from a tropical ocean weeks ago, carried north on wind currents, condensed into clouds, and finally frozen into this crystalline form. Some of these same water molecules might have been part of ancient glaciers, or might have fallen as rain in prehistoric forests, or flowed through rivers in distant lands. Water moves in a grand cycle through the Earth's systems, and snow is simply one phase in this eternal circulation, a temporary crystalline form in water's endless journey. As the snowflake descends through the lower atmosphere, conditions may change again. If it passes through a layer of warmer air, some of its delicate extensions might begin to round and smooth as the finest points sublime, returning directly from ice to vapor. If it passes through particularly moist air, it might develop a coating of rime, tiny frozen droplets that create a rougher, more opaque surface. The snowflake is continually shaped by its environment, right up until the moment it lands. The mathematics of snowflake formation have fascinated scientists for centuries. In 1611, the astronomer Johannes Kepler wrote an essay titled On the Six-Cornered Snowflake, puzzling over why snowflakes always had 6 sides. He couldn't know about the molecular structure of water, but he recognized that the consistent hexagonal shape must reflect some fundamental principle of nature. Centuries later, when scientists finally understood atomic structure, they realized Kepler's intuition was correct. The six-fold symmetry arises from the hexagonal arrangement of molecules in ice crystals, which itself arises from the angle of hydrogen bonds in water molecules. In the 1930s, a Vermont farmer named Wilson Bentley became the first person to successfully photograph individual snowflakes under a microscope. He captured more than 5,000 images over his lifetime, and through his patient work, the world could finally see the extraordinary diversity and delicate beauty of these tiny ice crystals. Bentley called them tiny miracles of beauty and noted that in all his years of observation, he never found two snowflakes that were identical. His photographs revealed that each snowflake was a unique masterpiece, crafted by the atmosphere according to rules that created both symmetry and infinite variation. The science of snowflake formation, called snow crystal morphology, reveals that the exact shape a snowflake takes depends on a precise combination of temperature and supersaturation, which is the amount of excess water vapor available in the air. Researchers have created morphology diagrams that predict what type of snow crystal will form under specific conditions. At -2 degrees with high humidity, you get thin plates. At -5 degrees, you get needles. At -15 with abundant moisture, you get the elaborate stellar dendrites. Each temperature and humidity combination produces its characteristic form, like a recipe that the atmosphere follows. But within these general patterns, infinite variation exists. The path each snowflake takes is unique, with countless micro-variations in temperature and humidity along the way. A snowflake might spend more time tumbling in one orientation, causing one side to grow slightly more than another. It might encounter a tiny pocket of turbulent air that changes its trajectory. These minute differences accumulate into the unique structure of each crystal. It's estimated that a typical snowflake experiences at least 1 trillion different conditions as it grows and falls, each one contributing to its final form. Some snowflakes develop hollow columns, forming hexagonal tubes like tiny glass pipes. Others grow as capped columns, with plate-like structures on each end of a columnar center, looking like tiny spools. There are triangular crystals, rare forms where only 3 of the 6 sides develop fully. There are bullet rosettes, clusters of columns joined at a central point like flowers made of ice. The variety seems endless, each form a response to specific atmospheric conditions, each one following the same fundamental rules but expressing them in a unique way. When snowflakes finally reach the ground, they begin a new phase of their existence. Fresh snow has a very low density, sometimes as light as 10% water and 90% air. The intricate structures of individual snowflakes create countless tiny spaces between crystals, trapping air and creating the fluffy texture of new snow. This trapped air makes snow an excellent insulator. Animals burrow into snow to escape the cold because the air pockets in the snow keep temperatures warmer than the air above. Indigenous peoples have built snow shelters for thousands of years, understanding intuitively what science has confirmed: snow's structure makes it protective. Over time, the delicate points and branches of snowflakes break down under the pressure of overlying snow in the subtle process of metamorphosis. The fine details that made each snowflake unique gradually disappear as the snow settles and compacts. The ice crystals change shape, becoming more rounded and uniform. This process can eventually create firn, a granular form of snow that is the intermediate stage between snow and glacial ice. If enough snow accumulates year after year without melting, it can compress into solid glacial ice over decades and centuries, with snow that fell in our lifetime eventually becoming part of ice sheets that flow and shape the landscape. remain frozen for thousands of years, becoming part of ice layers that record the history of the Earth's climate. Scientists drill ice cores from these ancient layers, finding snowflakes that fell during past ice ages, during periods of volcanic activity when ash settled on the snow, during times when the atmosphere had different compositions. Each layer of snow, now compressed into ice, is a page in the Earth's history book. The sound of falling snow is one of nature's subtlest experiences. Fresh snow absorbs sound because of all the air spaces between crystals, creating an unusual quiet. When you're in a snowfall, sounds become muffled and distances are hard to judge. The world feels closer and more intimate. This acoustic quality of snow has inspired countless poets and artists throughout history, capturing something essential about winter's character. The silence of snow is the silence of millions of tiny crystals creating millions of tiny sound-absorbing spaces. Different cultures have developed many words for snow, reflecting its importance in their lives. The Sami people of northern Scandinavia have numerous words distinguishing types of snow: snow falling through still air, wet snow, hard snow, soft snow, snow good for sledding, snow good for skiing. The Inuit languages similarly have many terms for snow in various states. These aren't just different words for the same thing. They're recognition that snow takes many forms, each with distinct properties and uses. Snow is not a single phenomenon, but a family of related conditions, each worthy of its own name. The formation of snow requires specific conditions: temperatures below freezing, sufficient moisture in the atmosphere, and ice nuclei to begin crystallization. This is why some cold places receive little snow. The interior of Antarctica, though bitterly cold, is actually a desert because the air is extremely dry. Snow forms most abundantly in places where cold air and moisture-laden air meet, like the regions downwind of large lakes or along mountain ranges where moist air is forced upward and cooled. The Great Lakes region of North America, the western slopes of Japan's mountains, and the alpine regions of Europe are all famous for heavy snowfall because they combine cold temperatures with abundant atmospheric moisture. Lake effect snow is a dramatic example of snow formation. When cold Arctic air moves across the relatively warm water of large lakes, it picks up moisture through evaporation. As this now humid air reaches the far shore and rises slightly, it cools, and the moisture condenses and freezes into snow. Cities downwind of the Great Lakes can receive several feet of snow from a single lake effect event, with snowfall rates reaching several inches per hour. The snow falls in narrow bands, sometimes just a few miles wide, creating dramatic differences in accumulation over short distances. Mountain snow forms through orographic lift, where wind pushes moist air up mountain slopes. As the air rises, it expands and cools, and its moisture condenses and freezes. The windward sides of mountains often receive enormous amounts of snow, while the leeward sides remain relatively dry in a rain shadow or snow shadow. Some mountain locations receive more than 50 feet of snow in a typical winter, creating snowpacks so deep that they persist through the summer and provide water for millions of people through the dry season. The timing of snowmelt is crucial for ecosystems and human societies. In many regions, snow that accumulates through winter forms a natural reservoir that releases water gradually through spring and summer. Rivers fed by snowmelt maintain flow during dry months, supporting agriculture, wildlife, and human communities. Changes in snow accumulation and melt timing due to climate change are affecting water availability, with earlier melts leading to water shortages later in summer and changes in river flow patterns affecting everything from salmon migration to irrigation scheduling. The albedo effect of snow, its ability to reflect sunlight, plays an important role in Earth's climate. Fresh snow can reflect up to 90% of incoming solar radiation, helping to keep polar regions cold. As snow ages and becomes dirty or begins to melt, its albedo decreases and it absorbs more heat, accelerating melting in a feedback loop. The extent of snow and ice cover affects global temperatures, making snow not just a local phenomenon but a component of the planetary climate system. Changes in snow cover are both a consequence of climate change and a factor that influences its progression. Some snowflakes encounter supercooled water droplets as they fall, droplets that are liquid despite sub-freezing temperatures. When a snowflake collides with these droplets, they freeze instantly onto the snowflake's surface in a process called riming. Heavy riming can completely obscure the original crystal structure, creating graupel, sometimes called soft hail or snow pellets. These are the small, opaque white balls that sometimes fall during winter storms, bouncing when they hit the ground. Graupel sits in the boundary between snow and hail, a hybrid form of winter precipitation. In rare conditions, snowflakes can develop into particularly large forms. The largest snowflakes ever recorded fell during a storm in Fort Keogh, Montana, in 1887, with reports of flakes 15 inches across. These were almost certainly aggregates of many smaller crystals clustered together, but they demonstrate how snow can sometimes form structures much larger than the typical quarter-inch to half-inch crystals we usually observe. Such giant snowflakes occur when temperatures are near freezing and snowflakes are slightly sticky, allowing them to adhere to each other as they fall. The phenomenon of thunder snow occurs when atmospheric conditions create the strong updrafts and electrical charging typically associated with thunderstorms, but temperatures are cold enough for precipitation to fall as snow rather than rain. Lightning flashes through falling snow, and thunder rumbles across winter landscapes, a rare and dramatic event. Thunder snow is unusual because the snow itself dampens sound, so thunder from thunder snowstorms is often heard only within 2 or 3 miles of the lightning strike, compared to 10 or more miles for summer thunderstorms. As we float in consciousness through this winter sky, observing snowflake after snowflake forming and falling, we can appreciate the profound complexity arising from simple rules. Water molecules, following the basic principles of chemistry and physics, create structures of remarkable beauty and infinite variety. No human art could match the complexity of a single snowflake, yet snowflakes create themselves by the billions, each one a small masterpiece, most of them falling unseen in remote places, melting without ever being observed, their brief existence and unique beauty experienced by no one. There's something philosophical in this, something that speaks to the nature of existence itself. Things of profound complexity and beauty arise constantly through natural processes, without intent or purpose, simply as consequences of physical laws working themselves out in matter. The snowflake doesn't know it's beautiful. It has no awareness of its symmetry or uniqueness. It simply is, for a brief time, before it melts and returns to the cycle of water moving through the world. Traditional knowledge about snow remains valuable alongside scientific understanding. Farmers watching the quality of snow can predict whether it will melt quickly or slowly in spring, affecting when they can plant. Mountain travelers reading the texture and layering of snow can assess avalanche danger. These skills, passed down through generations, represent accumulated wisdom about how snow behaves, complementing scientific understanding with practical knowledge earned through centuries of observation and experience. The crystals of snowflakes are so small and so cold that they're difficult to observe directly. They sublimate quickly when exposed to warm breath or warm surfaces, which is why catching snowflakes to examine them requires cold surfaces, special care, and often tools like chilled microscope slides or photographs taken rapidly before the delicate structures can change. Wilson Bentley worked in an unheated shed in Vermont winters, developing photographic plates with fingers numbed by cold, racing against sublimation to capture his images. Modern researchers use specialized equipment and controlled cold chambers, but they face the same fundamental challenge. Snowflakes are ephemeral by nature. Research into artificial snow creation has taught us much about snowflake formation. In laboratory settings, scientists can control temperature and humidity precisely, creating specific forms of snow crystals and observing how different conditions affect growth. These studies have confirmed the morphology diagrams and revealed finer details about how crystals develop. Interestingly, this research also has practical applications in improving artificial snow production for ski resorts, helping create snow that's more similar to natural snow in texture and performance. The weight of snow varies enormously depending on its water content and how compacted it is. Fresh, fluffy snow might have a snow water equivalent of just 5%, meaning a foot of snow contains only 0.6 of an inch of water. Heavy, wet snow might be 20 or even 30% water, making it much heavier and more difficult to shovel. This variation is why weather forecasts often distinguish between types of snow, warning about heavy snow that can weigh down trees and power lines, or light and fluffy snow that will blow and drift easily. As snow accumulates on the ground, it undergoes continuous transformation. Temperature gradients within the snowpack cause water vapor to move from warmer areas to colder areas, where it deposits and forms new crystal structures. This creates layers with different properties, some strong and stable, others weak and prone to collapse. Understanding these layers is crucial for avalanche forecasting. Avalanche professionals dig snow pits to examine the layering, testing the bonds between layers and identifying potential failure planes where avalanches might initiate. The beauty of snow has inspired art, literature, and music across cultures. Japanese haiku often reference snow as a symbol of winter's severity but also its beauty and purity. Impressionist painters captured the blue shadows in snow and the way snowlight illuminates landscapes. In literature, snow often symbolizes both death and renewal, covering the old world while providing the moisture that will feed spring growth. This dual nature of snow, both ending and beginning, has made it rich material for metaphor and meaning. In our minds, we can follow a single snowflake from its beginning as a dust particle floating in the upper atmosphere, through its encounter with supercold water and transformation into the seed of a crystal, through its elaborate growth as it falls through varying layers of cold, moist air, developing its unique structure branch by branch, side branch by side branch, then finally to its landing on the growing snowpack, where it settles among billions of its siblings, each one slightly different, together creating the white blanket of winter. The The sound of walking on snow changes with temperature and crystal structure. Warm snow near freezing is nearly silent underfoot, the crystals compacting quietly. Cold, fresh powder might squeak or crunch, the sound of brittle crystals breaking and grinding against each other. Very cold snow at temperatures well below zero creates the distinctive squeak that characterizes the coldest winter days, when each step seems to announce itself in high-pitched protest. These sounds are the voices of billions of ice crystals responding to pressure, each sound a tiny report of crystal fracture and friction. Night snow has its own quality, especially when falling under streetlights or moonlight. The flakes appear as points of light, descending through the darkness like earthbound stars. In cities, snow softens the harsh edges of buildings and muffles traffic noise, creating moments of unexpected quiet and beauty in the urban landscape. In wild places, snow under moonlight transforms familiar landscapes into unfamiliar territory, shadows deeper and distances deceptive, the whole world rendered in shades of blue and white. Children's first encounters with snow are often transformative experiences, the discovery that water can be solid and can be shaped, that you can catch the sky in your hands. Building snowmen, making snow angels, catching snowflakes on tongues. These simple interactions with snow create memories that last lifetimes. There's something fundamental in the human response to snow, a sense of wonder at this transformation of familiar water into something strange and beautiful, a phenomenon that seems to belong to both the ordinary world of weather and to the realm of magic. As our long journey through the story of snow and snowflakes draws toward rest, we can hold in mind the complete cycle. Water evaporates from oceans and lakes, rises into the atmosphere, condenses into clouds, freezes into snowflakes of infinite variety, falls to earth, melts and flows through streams and rivers, returns to the ocean, and begins the cycle again. Snow is not separate from rain or clouds or rivers or oceans, but part of one continuous circulation of water through the Earth's systems, moving through different states and forms but always the same water, the same molecules, cycling endlessly through sea and sky and land. Let the image of snowflakes falling settle into your mind as you settle into sleep. Each flake unique, each one following physical law but creating individual beauty. Falling silently through cold air, accumulating into drifts and blankets, transforming the world into something clean and new. The infinite variation arising from simple rules, the beauty emerging without intention, the temporary crystalline perfection of ice forming in the sky, all of this happening constantly, throughout every winter, across every place where the air grows cold enough, snowflakes forming and falling, each one a small miracle, together creating the phenomenon we know as snow. Let yourself drift now, like a snowflake, following your own path downward into rest, settling gently into sleep, where you can rest among all the other thoughts and dreams, each one unique, each one temporary, each one part of the larger cycle of consciousness rising and falling, appearing and dissolving, like snowflakes in their season, beautiful and brief and exactly as they should be. Rest now, in the quiet white peace of falling snow. As you continue to rest in this winter meditation, let us journey deeper into the science and wonder of snow, exploring the countless ways these frozen crystals shape our world and our understanding of nature itself. The formation of snow crystals follows patterns that appear throughout nature, patterns that mathematicians call fractals. A fractal is a shape that shows similar patterns at different scales, where each small part resembles the whole. When you look at a snowflake's branching structure, you you see this principle at work. The main arms branch off from the center, then smaller branches grow from those arms, and even smaller branches can grow from those. This self-similar branching appears in river systems, in lightning bolts, in the branching of trees and blood vessels, and in coastlines. Nature seems to favor these patterns because they're efficient ways to distribute material or energy through space. The snowflake, building itself molecule by molecule in the sky, follows these same elegant mathematical principles that govern so much of the natural world. When scientists study snow crystals under very high magnification, they discover that even the seemingly smooth surfaces of the ice crystal contain intricate molecular details. The surface of a growing snowflake is not perfectly still but is constantly active at the molecular level, with water molecules attaching and occasionally detaching, settling into the most stable positions. This molecular dance happens at a scale far too small to see, even with optical microscopes, but it's this activity that builds the crystal and gives it its form. In a sense, each snowflake is alive with molecular motion, even though it's frozen solid. The study of snow has practical importance beyond its beauty. Understanding snowfall patterns helps communities prepare for winter weather, plan snow removal, and manage water resources. In the western United States, water managers carefully monitor the snowpack in mountain ranges because melting snow provides the majority of water for cities and farms during dry summer months. They measure snow depth and snow water equivalent at monitoring stations throughout the mountains, building models to predict how much water will be available months later when the snow melts. The snow falling today becomes the drinking water and irrigation water of tomorrow. Snow crystals can become remarkably pure forms of ice. Unlike lake or river ice, which often contains trapped air bubbles, dissolved minerals, and impurities, snow crystals form directly from water vapor and can achieve very high purity. This is why fresh snow is safe to eat in wilderness settings, though urban snow should be avoided due to air pollution that the snow has collected. As snow falls through the atmosphere, it does collect some particles and dissolved gases, but the ice crystal itself is generally very pure water. Indigenous peoples and polar explorers have long melted snow for drinking water, understanding that fresh snow is essentially distilled water in frozen form. The color of snow, which we perceive as white, comes from its structure rather than from any pigment. Each ice crystal surface reflects and refracts light. When light enters a snowflake, it might reflect off internal surfaces, refract as it passes through, or reflect off the outer surface. Because snowflakes have complex three-dimensional structures with many surfaces at many angles, light bounces around inside and between crystals, scattering in all directions. This scattering of all wavelengths of light is what creates the white appearance. Deep snow can appear slightly blue, especially in shadows or in deep holes, because blue light penetrates ice better than red light, similar to why deep water appears blue. Different animals have evolved remarkable adaptations for life in snowy environments. The Arctic fox grows a thick white coat in winter that provides both camouflage and insulation. Snowshoe hares develop large, furry feet that distribute their weight and allow them to walk on top of deep snow rather than sinking through. Ptarmigans, birds that live in Arctic and alpine regions, grow feathered feet that act like snowshoes and turn white in winter to blend with snowy surroundings. These adaptations show how thoroughly snow shapes the evolution of species in regions where it dominates the landscape for much of the year. plants, too, have evolved strategies for surviving under snow. Many alpine and Arctic plants are low-growing, staying beneath the snow surface where they're insulated from the harshest winds and most extreme cold. The snow acts as a blanket, maintaining temperatures near 0 Celsius even when air temperatures far above drop to -40 or colder. Some plants actually benefit from snow cover, which protects them from freeze-thaw cycles that can be more damaging than constant cold. In spring, some flowers have evolved to bloom immediately after snowmelt, racing to complete their reproductive cycle in a brief window before other plants leaf out and shade them. The phenomenon of snow rollers, though rare, demonstrates wind's ability to shape snow in unusual ways. When conditions are just right, a thin layer of wet, cohesive snow on top of ice or hard-packed snow, combined with strong winds, the wind can pick up chunks of snow and roll them along the ground. As they roll, they accumulate more snow, forming cylinders that can grow quite large, sometimes several feet across. These snow rollers look like rolled hay bales made of snow, and they often have hollow centers because the inner layers are less compact. They appear spontaneously across fields after certain winter storms, creating landscapes dotted with these natural snow sculptures. Avalanches represent snow's power and danger. These rapid flows of snow down mountainsides can reach speeds of 80 miles per hour or more, carrying immense force. Avalanches occur when the bonds between layers of snow fail, often when a weak layer buried within the snowpack collapses under the weight of snow above it. The science of avalanche forecasting involves understanding the complex layering of the snowpack, current and recent weather conditions, terrain factors like slope angle and aspect, and countless other variables. Despite sophisticated forecasting methods, avalanches remain difficult to predict precisely, and they claim the lives of climbers, skiers, and mountain residents each year. The transformation of snow into ice and glaciers is a process that can take many years or even centuries. Fresh snow has a density of around 1/10 that of pure ice. As snow accumulates and is buried by successive layers, it's compressed by the weight above. Air is squeezed out from between crystals. Over time, usually a year or more, the snow transforms into firn, a granular form with density around half that of pure ice. With continued burial and compression over decades, firn gradually transforms into glacial ice with density approaching that of pure ice. Deep in large glaciers and ice sheets, this ice can be thousands of years old, having fallen as snow millennia ago and been slowly compressed and buried by subsequent snowfalls. Ice cores drilled from glaciers and ice sheets provide remarkable records of past climate. As snow falls and is buried, it traps tiny bubbles of the atmosphere. These bubbles are preserved as the snow is compressed into ice, creating samples of ancient air. Scientists can analyze these bubbles to determine the composition of the atmosphere when that snow fell, the levels of carbon dioxide, methane, and other gases. Ice cores from Antarctica contain ice more than 800,000 years old, providing a record of atmospheric composition spanning multiple ice ages. Layers in the ice also contain dust, pollen, volcanic ash, and other materials that fell with the snow, creating a detailed history of the planet's environmental conditions. Snow affects sound transmission in complex ways beyond just absorbing sound. fresh powder snow can reduce sound levels by as much as 60% compared to bare ground because the complex structure of loosely packed snowflakes creates countless surfaces that absorb sound energy. However, hard-packed snow or ice can actually reflect sound well, which is why sounds sometimes carry far across frozen lakes. Temperature inversions, which are common in winter when cold air is trapped beneath warmer air, can create conditions where sound travels unusually far, bending along the temperature boundary and carrying voices or noises across surprising distances. The role of snow in human history is profound. Before modern refrigeration, snow and ice were harvested and stored for use through summer. Ice houses, insulated structures filled with winter ice and snow, provided refrigeration for food storage. This ice trade was once a major industry, with ice cut from northern lakes shipped around the world. Snow has influenced military campaigns. Napoleon's retreat from Russia and the German invasion during World War II both suffered catastrophically from Russian winter conditions. Snow has shaped where people settled, what crops they grew, and how societies developed, with profound differences between cultures adapted to heavy snow and those from snow-free regions. Snow's importance in mythology and folklore spans cultures. Many traditions personify winter and snow as deities or spirits. The Japanese Yukiana is a spirit associated with snowstorms, appearing as a beautiful woman in white who leads travelers astray. Norse mythology features Skadi, a goddess associated with winter, skiing, and mountains. Many cultures have stories explaining the first snow or rituals to bring or banish winter. These stories reflect snow's power in human experience, its beauty but also its danger, its role as both preserver and destroyer, its association with purity but also with death. The physics of skiing and snowboarding depends on understanding how snow behaves under pressure and motion. When you ski, the pressure of your weight on the narrow ski creates a thin layer of water between the ski and the snow through a combination of pressure melting and frictional heating. This water layer acts as a lubricant, allowing the ski to glide. Different snow conditions require different ski waxes because the optimal glide characteristics change with temperature and snow crystal type. Cold, fine-grained snow behaves differently than warm, coarse-grained snow, and experienced skiers can read snow texture and adjust their technique accordingly. Frost flowers are a rare and delicate phenomenon that occurs on new sea ice in the Arctic. When very cold air contacts the slightly warmer surface of new ice, water vapor sublimates from the ice surface and immediately refreezes into delicate crystalline structures that grow upward. These formations look like small flowers or feathers made of ice, standing on the ice surface. They're extremely fragile and exist only briefly before being destroyed by wind or covered by snow. Frost flowers also concentrate salt from seawater, creating structures with salt content much higher than the surrounding ice, which has implications for understanding sea ice chemistry and atmosphere-ocean interactions in polar regions. Snow petrels are remarkable birds that live in Antarctica, one of only a few bird species that breed on the Antarctic continent itself. These pure white birds nest in crevices in rocky areas, and they spend much of their time over pack ice in open ocean. Their white plumage provides camouflage in the snowy environment, and they've adapted to survive in one of Earth's harshest climates. The presence of snow petrels far inland in Antarctica has been used by researchers to help locate meteorites, because the bird's presence indicates areas where wind has swept away surface snow, exposing dark rocks and potentially meteorites against the ice. The study of snow crystal formation has applications in understanding other crystallization processes. The same principles that govern snowflake growth also apply to how crystals form in metallurgy, how minerals precipitate from solutions, and how frost forms on surfaces. Research into snowflake formation has contributed to broader understanding of pattern formation, non-equilibrium thermodynamics, and how complex structures arise from simple rules. This is an example of how studying nature's beauty can lead to practical scientific understanding applicable far beyond the original subject. Snowflakes falling at night create a phenomenon that photographers call bokeh when caught in artificial light. Each snowflake appears as a disk or polygon of light, the shape determined by the camera lens's aperture. The collective effect of many snowflakes at different distances creates an abstract pattern of overlapping light shapes. This effect, while artificial, reflects something real about how light interacts with falling snow, each flake scattering and reflecting light, creating a dynamic, three-dimensional curtain of light and shadow moving through space. The sensation of snow on skin, of catching snowflakes and feeling them melt, connects us directly to the transformation of water between states. The cooling sensation comes from the heat energy required to melt the ice. The snow absorbs heat from your skin to undergo the phase change from solid to liquid. This same principle works at larger scales. Melting snow absorbs significant energy from the environment, which is why temperatures often remain near freezing until snow cover disappears. The presence of snow moderates temperature, keeping spring cooler than it would otherwise be until the snowpack is gone. Different regions have developed specialized vocabulary and knowledge about snow based on their experiences. Alpine guides distinguish between powder snow, spring snow, wind slab, sun crust, and many other snow types, each with different properties relevant to safety and travel. Indigenous peoples of the Arctic have detailed knowledge systems about snow that include not just types of snow but also wind patterns, ice conditions, and animal behavior related to snow cover. This traditional knowledge, developed over generations of careful observation, complements scientific understanding and often includes insights that Western science is only beginning to recognize and document. Snow plays a crucial role in the albedo effect that helps regulate Earth's temperature. Ice and snow reflect much more sunlight than darker surfaces like ocean water, forest, or bare ground. This means that the presence of snow and ice helps keep the planet cooler by reflecting solar energy back to space. As climate changes and snow cover decreases, this creates a feedback loop. Less snow means more heat absorption, which means warmer temperatures, which means even less snow. Understanding these feedback loops is essential for predicting future climate change, and changes in snow cover are among the most visible signs of a warming planet. The weight of accumulated snow can be enormous. In regions that receive heavy snow, buildings must be engineered to handle snow loads that can reach many tons on a single roof. Flat roofs are particularly vulnerable, and avalanches from roofs can be dangerous to people below. In Japan's snow country, where annual snowfall can exceed 30 feet, traditional architecture includes steep roof angles to shed snow and structural elements designed for heavy loads. Modern building codes in snowy regions specify snow load requirements based on historical records and statistical analysis of extreme snowfall events. Snow affects wildlife behavior in numerous ways. Many animals cache food before winter or build up fat reserves because foraging becomes difficult when snow covers the ground. Small mammals like mice and voles live in the space between the snow surface and the ground, called the subnivean layer, where temperatures remain relatively stable and they're protected from predators. Foxes and coyotes can often be seen plunging headfirst into snow, attempting to catch these small animals by listening for their movements beneath the snow and pouncing to break through. This hunting technique requires the predator to process acoustic information filtered through the snowpack, locating prey by sound alone. The science of snow dating, or determining when particular snow fell, is important in forensic science and archaeology. When an avalanche buries a person or when archaeological sites are preserved in snow or ice, understanding the timing can be crucial. Scientists can sometimes determine when snow fell by analyzing pollen, dust, or isotopic signatures in the snow and ice. The famous Otzi the Iceman, discovered in the Alps and preserved in ice for over 5,000 years, provides information about conditions when he died partly through analysis of the ice that preserved him. Snows of different densities produce different types of avalanches. Loose snow avalanches, also called sloughs, involve unconsolidated snow sliding downslope in a fan pattern. Slab avalanches, which are much more dangerous, occur when a cohesive plate of snow breaks free and slides as a unit, often fracturing along weak layers within the snowpack. These slab avalanches can be triggered by the weight of a single skier, by natural causes like warming temperatures or new snowfall, or by wind loading that deposits snow on lee slopes. The fracture in a slab avalanche can propagate across entire mountainsides in seconds, releasing enormous volumes of snow. The electrical properties of snow and ice have interesting effects. Blowing snow can generate static electricity through the friction of snow particles colliding with each other and with the ground. This can create electrical fields strong enough to cause corona discharge, a faint glow sometimes visible around sharp objects during snowstorms. Some researchers believe this electrical activity may play a role in nucleating new snow crystals by affecting how water molecules organize. Snow depth and snow water equivalent are related but different measurements. Snow depth is simply how deep the snow is, measured with a ruler or stake. Snow water equivalent is how much water the snow would produce if melted, typically measured by extracting a core of snow and weighing it. A foot of light powder might contain only an inch of water, while a foot of heavy wet snow might contain 3 or 4 inches. This distinction matters enormously for water resource management. What matters for water supply isn't how deep the snow is but how much water it contains. The phenomenon of depth hoar, a particular type of snow crystal that forms within the snowpack, creates dangerous avalanche conditions. Depth hoar forms when there's a strong temperature gradient in the snow, with much warmer temperatures near the ground than at the surface. Water vapor moves upward through the snowpack and recrystallizes into large, faceted crystals with weak bonds between them. These crystals look like sugar or ball bearings under magnification. A layer of depth hoar buried within a snowpack creates a weak plain where avalanches can initiate. this layer can persist throughout winter, creating ongoing hazard. Snow has acoustic properties that affect how animals communicate. The sound-absorbing nature of snow means that bird calls and animal vocalizations don't carry as far in winter as in summer. Some species adjust their vocalizations seasonally, calling more loudly or at different frequencies in winter. The snow surface also affects how sound reflects, with hard-crusted snow reflecting sound differently than soft powder. Predators and prey both must adapt to these changing acoustic conditions, which affect their ability to detect each other. The beauty of snow-covered landscapes has inspired countless artists. The Impressionists were particularly interested in snow scenes because they offered opportunities to explore reflected light and color in shadows. Claude Monet painted numerous snow scenes, observing that snow shadows aren't gray but contain blues, purples, and other colors reflected from the sky. Japanese woodblock artists like Hiroshige created famous series depicting snow scenes with different light and weather conditions. Photographers from Ansel Adams to contemporary artists have been drawn to the way snow transforms familiar landscapes into abstract compositions of form and light. Global snow cover is monitored by satellites, which provide daily data on where snow is present across the planet. This data reveals seasonal patterns, the advance of snow cover in autumn and its retreat in spring, and allows scientists to track changes over time. Satellite observations show that spring snow cover in the northern hemisphere has been decreasing over recent decades, with snow melting earlier and covering less area. This data provides crucial evidence for understanding climate change and its effects on the cryosphere, the portion of Earth's surface where water is in solid form. Snow crystals can form in clouds without ever falling to the ground, suspended on updrafts and growing to significant sizes before eventually either falling as precipitation or sublimating back into vapor as the cloud dissipates. These crystals can be carried long distances horizontally while remaining aloft, meaning that some snowflakes travel hundreds of miles through the atmosphere before landing, their structure recording a journey through vastly different conditions along the way. The timing of first and last snow varies dramatically with latitude and altitude. In equatorial regions, snow falls only on the highest mountains. In polar regions, snow can occur any month of the year. In temperate regions, there's typically a season when snow is common and other times when it's rare or absent. These patterns affect everything from agriculture to animal migration to human cultural practices. Changes in the timing of seasonal snow are among the most noticeable effects of climate change, with spring snow melting earlier and autumn snow arriving later in many regions. When snow melts, it doesn't disappear, it transforms. The water that was briefly organized into intricate crystalline structures becomes liquid, flowing into soil, streams, and groundwater. This meltwater carries nutrients that accumulated in the snowpack, delivering a pulse of water and nutrients to ecosystems in spring. The timing of snowmelt is crucial for plants and animals that have evolved to take advantage of this seasonal flood of resources. Wildflowers bloom, baby animals are born, and birds arrive from migration, all timed to the period of maximum resource availability that follows snowmelt. Let yourself rest with these images and ideas, drifting through understanding as snowflakes drift through air. Each fact another crystal of knowledge, each idea another facet of understanding. understanding. The science and beauty of snow interweaving like the branches of a snowflake, each supporting the other, creating a structure of understanding that is both logical and beautiful, both precise and mysterious. Let your mind settle like snow settling on the ground, layer upon layer, building depth, building quiet, building rest. As you sink deeper into sleep, imagine the vast extent of winter across the planet. Snow falling in mountains and across plains, accumulating in polar regions, transforming landscapes from green and brown to white. Each snowflake unique, each one following the same rules but expressing them differently, infinite variation within fundamental order. This is the pattern of nature itself, simple principles creating endless complexity, laws that produce freedom, structure that enables beauty. Snow teaches us about transformation, about how things change form but remain themselves. Water becomes snow becomes water again, cycling endlessly. Nothing is truly created or destroyed, only transformed, moving through the world in different forms, each form temporary, each form perfect for its time and place. Rest now in winter's quiet, in the peace of falling snow, in the gentle accumulation of moments like the accumulation of snowflakes, building toward morning, building toward spring, but for now simply being, simply falling, simply at rest in the deep silence of winter night. As we continue deeper into our meditation on snow, let us explore even more dimensions of how these frozen crystals shape our world, our understanding, and our experience of winter's profound presence. The process of sintering, where ice crystals bond together over time, transforms loose snow into more cohesive structures. Even without melting, ice crystals in contact with each other will gradually form bonds through a process where molecules migrate from areas of high stress to areas of lower stress. This is why snow that has sat for a few days becomes more compact and stable than fresh snow, even if temperatures remain below freezing. The individual crystals grow together, forming bridges between them, creating a more unified structure. This natural engineering process is what allows snow to support weight better over time and is essential for the formation of snow bridges over crevasses and the stability of snow slopes. In the world's coldest regions, snow takes on properties that seem almost otherworldly. At temperatures below -40 degrees Celsius, snow becomes extremely fine and dry, more like powder than the snow of milder climates. This cold smoke snow can be blown by even gentle winds, creating ground blizzards where visibility drops to near zero even under clear skies. The crystals at these extreme temperatures are often simple hexagonal plates or columns because the air is too cold and dry for elaborate dendrites to form. Walking through this ultra-cold snow produces that distinctive squeak with every step, a sound caused by the fracture of countless rigid crystals unable to deform in the extreme cold. Snow measurement has evolved from simple rulers to sophisticated technology. Snow pillows, large flat bladders filled with antifreeze solution, sit on the ground and measure the weight of snow above them, automatically calculating snow water equivalent. Cosmic ray sensors measure snow depth by detecting how much cosmic radiation is absorbed by the snowpack. More snow means less radiation reaches the sensor. Automated weather stations in remote mountains send real-time snow data via satellite, allowing scientists and water managers to monitor snowpack missions across vast areas without ever visiting the sites. Despite this technology, there's still value in human observation, as experienced observers can assess snow quality, layering, and conditions in ways that automated sensors cannot fully capture. The relationship between snow cover and permafrost is complex and important. Snow acts as an insulator, and the thickness and duration of snow cover affect ground temperatures. In the Arctic, where permafrost exists, changes in snow cover can affect whether permafrost thaws or remains frozen. Thicker or longer-lasting snow cover keeps the ground warmer in winter, which can contribute to permafrost degradation. Conversely, reduced snow cover allows ground to freeze more deeply. These interactions create feedback loops that affect Arctic ecosystems, infrastructure built on permafrost, and the release of greenhouse gases from thawing permafrost soils. Hoarfrost, often confused with snow, is actually a different phenomenon. While snow forms in clouds and falls from the sky, hoarfrost forms when water vapor deposits directly onto surfaces, typically on cold, clear nights when surfaces cool below the dew point. Hoarfrost creates delicate feathery crystals on grass, tree branches, and any exposed surface. These crystals can be quite elaborate, forming intricate patterns similar to snowflakes but growing outward from surfaces rather than falling from above. On very cold mornings, entire landscapes can be coated in hoarfrost, creating scenes of extraordinary delicacy where every twig and blade of grass is outlined in crystalline ice. The snow line, the elevation above which snow persists year-round, varies dramatically around the world. Near the equator, the snow line exists above 18,000 feet, high in the Andes and on the highest African mountains. In polar regions, the snow line can be at sea level. This variation reflects differences in temperature with latitude, but also differences in precipitation. Wetter regions can maintain glaciers at lower elevations than drier regions because more snow accumulates. The position of the snow line has moved upward in many mountain ranges over recent decades, a visible indicator of warming temperatures. Glaciers that once reached lower elevations have retreated to higher, colder areas. Snow crystals can form in fog, creating a phenomenon called rime ice. When supercooled fog droplets contact cold surfaces, they freeze instantly, building up deposits of ice on the windward side of objects. Rime ice has a white, opaque appearance and can build out into fantastic shapes, creating spikes and fins extending into the wind. On mountain summits where fog and strong winds are common, rime ice can coat everything, rocks, equipment, buildings, with thick layers of ice that grow into elaborate formations. This isn't technically snow, but it's closely related, another way that water vapor in the atmosphere can create frozen beauty. The sport of ice climbing involves ascending frozen waterfalls and ice formations, and the quality of the ice depends largely on how it formed. Ice that formed from snow compaction is usually more opaque and less strong than ice that formed from freezing water. The best ice for climbing typically forms when water seeps and drips over rock faces, freezing in layers, creating dense, clear ice. But understanding snow is still crucial for ice climbers because snow accumulation on ice affects safety. Snow can hide hazards, create avalanche danger on slopes above ice routes, change the character of approaches to climbs. Snowfall records demonstrate the incredible variability in winter weather. The Mount Baker ski area in Washington state recorded 95 feet of snow in the winter of 1998 to 1999, the most ever measured in a single season. Paradise Ranger Station on Mount Rainier has an average annual snowfall of over 50 feet. In contrast, some continental interiors at high latitudes receive very little snow because the air is too cold and dry. Antarctica's interior is technically a desert despite being covered in ice. These extremes show how snow distribution depends on complex interactions between temperature, moisture, and geography. The grain size and shape of snow crystals changes over time through metamorphism. Fresh snow consists of crystals with their original forms, dendrites, needles, plates, but these detailed shapes don't last. Wind breaks crystals into fragments. Temperature gradients cause water molecules to migrate from smaller crystals to larger ones through sublimation and redeposition. Eventually, the snow becomes more granular, consisting of rounded particles rather than intricate crystals. This is the snow of spring, corn snow as skiers call it, made of coarse rounded grains that form through many cycles of slight warming and refreezing. Understanding snow metamorphism is crucial for avalanche forecasting and for understanding how snowpack evolution affects water storage. Sacred mountains around the world are often snow-covered, and snow plays important roles in many religious and spiritual traditions. In Hinduism, the Himalayas, whose name means abode of snow, are considered the dwelling place of gods. Mount Kailash, permanently snow-covered, is sacred to multiple religions. In Shinto tradition, Mount Fuji's snow-covered peak is iconic and spiritually significant. Indigenous peoples of the Americas often have sacred peaks that are snow-covered, seeing spiritual significance in the eternal snow. This association between snow-covered mountains and the sacred appears across many cultures, perhaps reflecting how these high, pure, cold places seem to exist between earth and sky, in a realm apart from ordinary life. The density of snow increases with depth in a snowpack due to compaction. Surface snow might have a density of 100 kilograms per cubic meter, while snow at the bottom of a deep snowpack might reach 400 kilograms per cubic meter or more. This densification happens because the weight of overlying snow compresses the lower layers, squeezing out air and allowing crystals to pack more tightly. In glaciers and ice sheets, this process continues for years or centuries until the density approaches that of pure ice at around 900 kilograms per cubic meter. Snow affects aircraft in multiple ways. Snow accumulating on wings and control surfaces changes their aerodynamic properties and adds weight. Blowing snow reduces visibility for takeoffs and landings. Snow and ice crystals can damage engine components or be ingested into engines. Modern aircraft are equipped with de-icing systems, heated surfaces, chemical de-icers, pneumatic boots that flex to crack ice, to handle winter conditions. Airports in snowy regions maintain large fleets of specialized equipment for snow removal, because even a few inches of snow can shut down operations if runways and taxiways aren't clear. The formation of snow cornices, overhanging formations of wind-deposited snow along ridges, create creates beautiful but dangerous features in mountain terrain. As wind blows across a ridge, it deposits snow on the lee side, building out a structure that extends beyond the underlying ridge. Cornices can grow to enormous size, sometimes extending 30 feet or more beyond the ridge. They're hazardous because their extent is often not visible from above. A climber might think they're on solid ridge when they're actually on an overhanging cornice that could collapse. Cornices eventually fail under their own weight, sometimes triggering avalanches on slopes below. Snow plays a role in cloud seeding, the process of inducing precipitation by introducing particles into clouds. Silver iodide has a crystal structure similar to ice, making it an effective ice nucleus. When silver iodide particles are introduced into supercooled clouds, they can trigger ice crystal formation and snow development. Cloud seeding is used in some regions to increase snowfall in mountains, potentially increasing water supply. The effectiveness of cloud seeding is still debated. It's difficult to prove how much additional precipitation results, but under favorable conditions, seeding can increase snowfall by perhaps 10 to 15%. In poetry and literature, snow often symbolizes silence, purity, erasure, and transformation. The blank page of new snow suggests new beginnings and the covering of past events. The silence of snowfall creates contemplative mood in countless poems and stories. Robert Frost's Stopping by Woods on a Snowy Evening captures the meditative quality of watching snow fall in quiet woods. James Joyce's The Dead ends with a famous passage about snow falling across Ireland, suggesting how snow makes universal and equalizes all things beneath it. These literary uses of snow reflect its real qualities, its quieting effect, its transformation of the landscape, its association with both beauty and coldness. The study of past snowfalls preserved in ice provides climate data extending back hundreds of thousands of years. Annual layers in ice sheets can be counted like tree rings, and the thickness of each layer indicates how much snow fell that year. The isotopic composition of the ice reflects the temperature when the snow fell. Water molecules containing heavier oxygen isotopes precipitate preferentially at different temperatures, so the ratio of isotopes in ice indicates past temperatures. Dust, volcanic ash, and other materials trapped in annual layers provide additional information about past environmental conditions. These ice core records reveal natural climate cycles and provide context for current climate changes. Snow enhances ultraviolet radiation exposure through reflection. Fresh snow can reflect 80 to 90% of UV radiation, essentially doubling exposure for anyone on snow-covered surfaces. This is why snow blindness occurs. Intense UV exposure damages the cornea, causing pain, light sensitivity, and temporary vision loss. Mountaineers, skiers, and Arctic travelers must wear protective eyewear to prevent snow blindness. This high reflectivity is also why you can get sunburned more easily on snow, and why spring skiing often results in distinctive tan lines from goggles and clothing. The way snow loads trees affects forest structure and ecology. Heavy wet snow can break branches or topple entire trees, creating gaps in forest canopies that allow light to reach the forest floor. This natural disturbance shapes forest structure and creates habitat for species that need openings. Some trees trees have evolved forms that shed snow effectively, conical shapes that allow snow to slide off, flexible branches that bend under snow weight without breaking. Other trees in less snowy climates are more vulnerable to damage from unusual snow events. The ice storm or heavy snow that rarely occurs can cause more damage than regular heavy snow in areas where trees have adapted. Neve is the term for old, granular snow that has survived one melt season and is beginning its transformation into glacial ice. It's denser and coarser than seasonal snow, but not yet as dense as glacial ice. Neve fields exist on mountains at high enough elevations that not all winter snow melts each summer. These perennial snow fields are important for mountaineering, providing snow routes up peaks in late summer when lower elevations are snow-free, and they're indicators of climate conditions. Neve lines moving upward on mountains indicate warming temperatures and reduced snow accumulation. The migration of the Arctic tern, which flies from Arctic to Antarctic and back each year, means these birds experience two polar summers but no polar winter. They experience summer's midnight sun in both hemispheres but avoid the dark, snowy winters. Many bird species migrate to avoid winter and snow cover, which eliminates food sources like insects and makes seeds difficult to access. The presence or absence of snow cover triggers migration for many species. Earlier snowmelt leads to earlier migration for some species, while earlier snowfall triggers earlier autumn migration. These phenological changes, shifts in the timing of seasonal events, are among the most widespread effects of changing climate. Snow is featured in famous expeditions and explorations. The race to the South Pole between Roald Amundsen and Robert Scott involved crossing hundreds of miles of snow and ice. Amundsen's success and Scott's tragedy depended partly on their different approaches to snow travel. Amundsen used skis and dog sleds, while Scott relied more on man-hauling. Ernest Shackleton's remarkable survival story after the loss of the Endurance involved crossing South Georgia Island, mountainous and snow-covered, to reach a whaling station. These exploration stories involve triumph and tragedy played out against snowy landscapes that tested human endurance and ingenuity. The insulating properties of snow protect soil organisms and plant roots from extreme cold. Beneath the snow, temperatures remain relatively constant near 0 Celsius, even when air temperatures drop far below zero. This subnivean environment supports active ecosystems throughout winter. Bacteria, fungi, and small invertebrates remain active in soil beneath snow. Some plants actually photosynthesize under snow. Evergreen plants can absorb light that penetrates snow cover and conduct limited photosynthesis. The snow cover creates a protected winter environment that, while cold, is far more stable and moderate than the harsh, fluctuating conditions above the snow surface. Snowpack development follows predictable patterns in most regions. Early season snow often melts completely between storms. As winter progresses and temperatures drop, snow begins to accumulate. Midwinter typically brings the deepest, coldest snow. Late season snow is often wetter and denser as temperatures warm. Spring brings the melt season, when the snowpack becomes isothermal at 0 Celsius and begins to release water. These patterns vary by region. Some areas have consistent snow cover from first snow to spring melt, while others experience multiple accumulation and melt cycles through winter. Wilderness survival in snow requires understanding how snow can be both resource and hazard. Snow can be melted for water, though this requires fuel and time. Snow caves or igloos can provide emergency shelter, using snow's insulating properties. But snow also draws heat from the body through conduction, and staying dry is critical. Wet clothing loses insulating value. Wind-blown snow can create whiteout conditions where it's impossible to navigate. Avalanche danger makes some terrain impassable. Experienced winter travelers develop skills for moving through, living in, and reading snowy environments, understanding both snow's protective and dangerous qualities. The interface between snow and ground, called the basal layer, has unique properties. This is where heat from the ground meets the cold of the snowpack. Temperature gradients are often strongest here, leading to the formation of depth hoar and other weak layers. This is also where small mammals create their subnivean tunnels, and where many processes of decomposition and soil activity continue through winter. The basal layer is neither quite snow nor quite ground, but a transitional zone with its own characteristics. Snow chemistry studies how snow interacts with and transports pollutants. Snow falling through the atmosphere scavenges particles and gases, accumulating pollutants. In some regions, the first major snowmelt pulse delivers a concentrated dose of pollutants accumulated over winter into streams and lakes. This pulse can affect aquatic ecosystems. Snow also preserves chemical signals. Pollutants in snow layers can indicate past industrial activity, atmospheric nuclear testing, or volcanic eruptions. Ice cores from Greenland show lead pollution from ancient Roman mining, demonstrating how snow archives human environmental impacts over millennia. Snowshoes, developed by indigenous peoples in North America and Asia, demonstrate engineering solutions to the challenge of moving through deep snow. By distributing weight over a larger area, snowshoes allow travel on top of snow that would otherwise require exhausting post-holing. Traditional snowshoe designs vary by region and snow conditions. Some are elongated for open terrain, others are rounded and more maneuverable for forests. Modern snowshoes use different materials but follow the same principles. Increase the surface area of the foot to reduce pressure and prevent sinking through snow. The aesthetic of snow in gardens and landscapes has been cultivated in different ways across cultures. Japanese gardens are often designed with winter in mind, incorporating evergreens and structural elements that are beautiful when highlighted by snow. The practice of yukimi, snow viewing, is an aesthetic appreciation of snow-covered landscapes. In Western tradition, winter gardens might emphasize bark texture, persistent fruits, and evergreen structure that remain visible and attractive when covered with snow. These design traditions reflect snow's capacity to transform familiar spaces into temporary sculpture, with each branch and surface defined by its coating of light. Glacial lakes, formed by meltwater from glaciers, have distinctive colors ranging from gray to bright turquoise. The color comes from glacial flour, extremely fine particles of rock ground by the glacier and suspended in the water. These particles scatter light, with the finest particles creating the most vibrant turquoise colors. The same process process that creates snowflakes, the freezing of water, eventually creates the ice that forms glaciers, which grind rock into these fine particles, which create lakes of remarkable color. It's a progression from delicate ice crystal to massive grinding force to optical beauty. The winter solstice, the shortest day and longest night of the year in each hemisphere, occurs in the midst of winter for temperate and polar regions. Many cultures have celebrated this turning point, recognizing it as the moment when days begin lengthening again, when the return of light begins even as winter deepens. The solstice often coincides with maximum snow cover in many regions, though the coldest temperatures typically come later. This disconnect between the solar minimum and the temperature minimum occurs because Earth's systems have thermal inertia. Oceans and land continue cooling for weeks after the solstice, and the coldest winter weather often comes in January or February in the northern hemisphere. Let your thoughts settle like snow in calm air, drifting gently downward, accumulating in layers, each thought its own crystal of understanding, unique but similar to all others, different in detail but following the same fundamental patterns. The facts about snow are like snowflakes themselves, individual pieces that collectively create something larger, a landscape of understanding, a field of knowledge, endless in variation yet unified in essence. As you rest in this meditation on winter, feel the peace that snow brings to the world. The quieting of sound, the softening of sharp edges, the transformation of the ordinary into something strange and beautiful. This is what understanding does as well. It transforms the familiar into something rich and complex, revealing depths we hadn't noticed, patterns we hadn't seen, connections we hadn't recognized. Snow teaches patience. It accumulates slowly, crystal by crystal, storm by storm. It melts gradually, feeding streams over weeks and months. It transforms over time, each day different from the last. This patience is built into winter's nature, and it's a lesson we can carry with us, that profound changes occur through accumulation, that time transforms all things, that patience and process create outcomes that haste cannot achieve. Breathe slowly, like wind moving across a snow field, steady and calm. Each breath is like a small storm, bringing slight change, but over many breaths, creating transformation. Rest in the knowledge that winter will pass, that snow will melt, that cycles continue. But for now, in this moment, rest in winter's peace, in the quiet beauty of snow, in the gentle accumulation of rest, building like a snowpack builds, layer upon layer, deepening your rest, deepening your peace, until you rest in the profound quiet of deep winter sleep. And so our long journey through the world of snow draws to its gentle close, though you may have drifted into sleep long ago, and if so, that is perfect. If you're still here, still listening, know that you've traveled with us through clouds and crystals, through science and beauty, through the endless variations of frozen water that transform our world each winter. We've witnessed the birth of snowflakes in the cold heights of the atmosphere, seen how water vapor gathers around tiny particles of dust and pollen, watched as molecules arrange themselves into hexagonal patterns dictated by the very nature of water itself. We've followed these delicate crystals on their journey downward, tumbling through layers of varying temperature and humidity, each one recording its unique path through the sky in its structure, in its branches, in the intricate details that make it different from every other snowflake that has ever fallen or ever will fall. snowflakes are both perfectly symmetrical and infinitely varied, that they follow rigid physical laws yet create endless beauty, that they are temporary yet part of an eternal cycle. In this, they mirror something essential about existence itself, how order and chaos dance together, how simplicity gives rise to complexity, how transient things participate in permanence. Think of all the snowflakes falling at this very moment, somewhere in the world. Even now, in the depths of summer in some places, snow is falling on high mountains. In polar regions, snow falls across vast ice sheets. In winter storms across temperate lands, billions upon billions of snowflakes are forming, falling, landing, each one unique, each one following its own path from cloud to ground. This is happening continuously, has been happening for as long as Earth has had cold places and moisture in its atmosphere, will continue happening into the distant future. You are resting now while snow falls somewhere. While you breathe slowly, deeply, drifting toward or dwelling in sleep, snowflakes are crystallizing in cold clouds. While your body rests and repairs itself through the night, snow is accumulating on mountains, in forests, across tundra. The world continues its cycles, and you are part of these cycles, waking and sleeping, activity and rest, just as water cycles between vapor and liquid and solid, just as seasons cycle between summer and winter. There's something deeply peaceful in knowing that these natural processes continue whether we observe them or not. Snowflakes form and fall in remote places where no human eye will ever see them. They create beauty that exists for its own sake, not for any observer. This happens in darkness and in light, in storm and in calm, constantly, naturally, following the simple rules that govern how water molecules arrange themselves when frozen. Let this thought settle into your rest. You don't have to do anything for the world to work. The snowflakes don't need your attention to form their perfect hexagons. The seasons don't need your worry to progress. Your own body knows how to rest, how to heal, how to prepare for tomorrow, all without your conscious effort. You can let go. You can trust in processes that are older and wiser than thought. As you rest, your breathing has probably become very slow, very regular. This is your body's wisdom, knowing what it needs. Like snow accumulating silently through a long winter night, your rest is accumulating, deepening, bringing you the restoration you need. There's no effort in this, no striving. Sleep, like snow, cannot be forced. It comes in its own time, settles in its own way. If you're still awake, there's no pressure to sleep. Sometimes rest itself is enough, lying quietly, breathing slowly, allowing thoughts to drift like snowflakes on wind. Your mind might wander to the things you learned tonight, to images of snowflakes in winter landscapes. Or your mind might wander to other things entirely, and that's fine too. Wherever your thoughts go, they're becoming softer, quieter, like sounds muffled by falling snow. Picture once more a winter landscape at night. Snow covers everything, trees, ground, rocks, buildings, transforming the familiar into something dreamlike. The moon perhaps shines through clouds, casting blue light across the white world. Or perhaps it's dark, with snow visible only as a texture, a presence, a quiet blanket drawn over the sleeping earth. The air is still. No sound but perhaps the distant call of an owl, or wind whispering through pine branches, or the soft sound of snow itself falling, a whisper so quiet it's almost imagined. You are safe and warm, watching this this scene from within shelter, or perhaps you are part of the scene itself, resting beneath the snow like a seed waiting for spring, like a bear in its winter den, like the earth itself in its seasonal sleep. Winter is a time of rest, of conservation, of going inward. Even as we understand the science of snow, we can honor this ancient rhythm of rest that winter represents. The snowflake's journey from cloud to ground takes perhaps 20 minutes, sometimes longer. Your journey into sleep might take minutes or hours, and either way is exactly right. There's no schedule to keep, no destination to reach. Like a snowflake, you're following your own unique path, responding to conditions around you and within you, eventually settling into rest in your own time and way. All the facts and stories we've explored tonight, the molecular structure of ice crystals, the formation of different snow types, the role of snow in ecosystems and climates, the way snow transforms landscapes and affects lives. All of this is interesting, but more than that, it's a meditation on pattern and process, on how the universe works at scales from molecular to planetary. Understanding these things can bring a sense of perspective, of connection to something larger than our individual concerns. You are made of water, just as snowflakes are made of water. The water in your body has cycled through the environment countless times, has been rain and snow, has flowed in rivers, has been clouds and ice and ocean. You are not separate from the natural world but part of it, made of the same substance, following the same fundamental laws, participating in the same great cycles. This connection is worth resting in, worth feeling, worth accepting. Let go now of any remaining thoughts that don't serve your rest. Let them drift away like snowflakes carried off by wind. What remains is simple: your breath, your body, your being at rest. The complexity we've explored tonight, all those intricate crystal structures, all those atmospheric processes, all those ecological interactions, all of it ultimately comes down to simple things: molecules arranging themselves according to their nature, water cycling through its forms, energy flowing through systems. Your rest, too, is simple. Breathe in, breathe out. Let go, settle down. Trust that sleep will come when it comes, and until then, rest is enough. You've given yourself this time to be still, to learn about something beautiful, to let your mind wander through winter landscapes and crystalline structures. This itself is a gift to yourself, this quiet time, this permission to simply be. The snow continues to fall in our imagination, in our story, perhaps in reality somewhere in the world as you listen to this. Each flake unique, each one perfect, each one temporary but part of something eternal. You, too, are unique, temporary in form but part of something that continues. This moment of rest is temporary, but rest itself is eternal, something all living things do, something the earth itself does in its seasons. As we come to the end of this long meditation on snow, carry with you whatever resonated, whatever brought you peace. The image of snowflakes forming in clouds, the silence of falling snow, the way snow covers everything equally, making no distinctions, the patient accumulation of crystals into drifts and fields of light, the transformation that comes with winter and the renewal that waits in spring. Sleep now or rest in stillness. Let yourself be held by the night, by the darkness, by the warmth of your bed or chair. Imagine that you're a snowflake that has completed its journey, that has landed softly, that now rests with countless others, part of something larger and more beautiful than any single crystal could be alone. Together, all these snowflakes create the phenomenon of snow, and together, all your moments of rest create the restoration your body and mind need. Breathe softly. Rest deeply. Let go completely. The story is complete, but your rest continues. The snow falls, the earth turns, the seasons cycle, and you rest in the midst of it all, safe and still and at peace. Good night. May your sleep be as peaceful as new fallen snow, as deep as winter's quiet, as restorative as the dormancy that prepares for spring's return. Rest well in winter's gentle embrace,